So a few days ago, we talked about the fundamental theorem of calculus. This is part 2 of the fundamental theorem of calculus. We're going to talk about integrals that are defined by functions. So if you look at this example here, you see at the top that instead of this being a number, it's a function. So we're going to talk about what would happen if we evaluate this. So the first thing we're going to do is just evaluate as it is. What I would do is go ahead and find the integral of t squared. So I get t cubed over 3. We're supposed to evaluate from 0 to sine x. So I just plug in the sine x first. So I get sine cubed x over 3 minus, sorry about my dogs, over, and then I plug in 0. 0 cubed over 3 is just 0. So that gives me 1/3 sine cubed x. So sorry about the dogs. All right, so this g of x was equal to this integral, but this integral equals this. This is also g of x. So now they want us to take the derivative of this. So take the derivative of g of x. Well, if they'd asked us to take the derivative of this from the beginning, I'm not sure we would have known what to do, but now that g of x looks like this, we know how to take the derivative of that. So I'm going to rewrite this as 1/3 sine x to the third, and we're going to take the derivative. So bring down the 3 times 1/3. So we just get sine x to the second times the derivative of the inside, which is going to be cosine x. So the second fundamental theorem of calculus, or the fundamental theorem part 2, is going to give us a shortcut for doing this. There's a way to do this that is a little shorter, and we're going to find that by just doing a general equation similar to the one at the top, where our integral here is some function, from a constant to some function. So all of this is going to be a little abstract because we don't have any numbers to deal with here. But the first thing we did was figure out what this function was before. So h of x would equal f of, and then we plugged in g of x minus f of a. Okay? So that's what we learned a couple of days ago. That this is just the first fundamental theorem of calculus. All right. So we know that h of x equals this as well. So now I want to find my derivative. That was the next piece. So when I take the derivative, this is a composition of functions. So it would be the derivative of the outside, inside stays the same, times the derivative of the inside. All right, minus, and then over here, this is just a constant. So that's just going to be 0. Derivative of a constant is 0. So what we have now is that h prime of x equals f prime of g of x times g prime of x. All right, so let's look at this little notation here. Capital F prime, or the derivative of the capital F, is just going to be little f. This right here is just going to be f of g of x. When you take the derivative of the integrated function, this is what it used to be. I take the derivative, I go back to what it was. So now I've got just f of g of x times g prime of x. So this is the shortcut. So let me show you how that works with the example we had up there above. we had g of x equals the integral from 0 to sine x of t squared, right? So if we use the shortcut, it says that g prime of x would equal, and we're going to put g of x, this function, this top value, in here. So we're going to get sine of x squared. So we just put g of x, this function, into our function inside, times the derivative of g, this top function. So the derivative of sine is cosine. And if you'll look, that's what we got up here at the top. Okay. So the second fundamental theorem of calculus just says that if we are evaluating an integral that goes from a constant, it doesn't have to be zero, any constant to a function, then all you have to do, if you're looking for the derivative of this identified function, is plug in the function at the top into your integrated function and then times its derivative. All right, so in this box it says what maybe I didn't say quite as clearly as they do in the box, but anyway, all we have to do is plug this in here times the derivative. So plug this in times the derivative, and that's it. Now this only works if they're asking you to find f prime, so don't get that confused with them just wanting you to evaluate a function that is defined as an integral, because they may just want you to evaluate and not find the derivative, like we did in the first step of the very first equation. So just be careful. They have to be asking you to find the derivative for this fundamental theorem of calculus part 2 to even work. So here we go. So the theorem says that all we have to do is plug this in to our function. So f prime of x is going to equal 1 over 1 plus the square root of 1 minus x squared. Just put x squared right here, times the derivative of x squared, which is 2x. Or we get 2x over 1 plus the square root of 1 minus x squared. Very, very simple to use. All right, let's look at the next example. The derivative of f would be sine of, we put x cubed in here, so x cubed squared times the derivative of this, which is 3x squared. So we get 3x squared sine of x to the power 2 power u multiply 6. All right, so let's look at our last example. In this last example, we have a problem. Remember that the fundamental theorem of calculus part 2 can only be used when we are evaluating from a constant to a function. This one goes from a function to a function. So I can do it, but I have to do it the long way, the way we did the very first problem. So the first thing we want to do is evaluate the integral. Just find out what f of x is equivalent to. So this is going to be 2t squared over 2. So we just get t squared. And we're going to evaluate that from x to x plus 1. So I get x plus 1 squared minus x squared. Well, x plus 1 squared is going to be x squared plus 2x plus 1, and then minus x squared. And so f of x just equals 2x plus 1, because those are going to go away. So that's the first part. But remember, after that, they ask us still to find the derivative. So now that I know that f of x is also equal to 2x minus 1. So this and this are equivalent to each other. Then I can take the derivative, and I just get 2. So not a difficult problem to do, but the shortcut does not work. You have to be going from a constant to a function to use the shortcut.